we present Instruct, Not Assist, LLM-based multi-turn planning and hierarchical questioning for Socratic code debugging. State-of-the-art large language models have been fine-tuned to be customer-serving and assistant-like. However, many domains require a model to be collaborative and challenging when beneficial to the user. This is clearly evident in education. Existing LLMs often give away solutions to students directly, making them ineffective instructors. On the other hand, existing education research argues that Socratic questioning is an effective teaching strategy, where a student is guided towards solving a problem on their own instead of just being given the solution directly. Thus, can we guide an assistant to ask Socratic questions that 1. Help the student understand their mistakes, and 2. Do not directly provide the answer? We tackle this issue in the code debugging domain with TreeInstruct, an instructor agent guided by a novel state-space-based planning algorithm. TreeInstruct asks probing questions to help students independently identify and resolve errors. It estimates the student's conceptual and syntactical knowledge to dynamically construct a question tree based on their responses and their current knowledge state. TreeInstruct utilizes this tree to effectively plan its conversation and address the student's independent and dependent mistakes concurrently in a multi-turn interaction setting. We split the typical teacher's tasks into 2 roles: the student-facing instructor and the internally planning verifier. With these agents, we break down our methodology into 3 core components. First, state space estimation. Here, the verifier estimates the set of conceptual and syntactical tasks for the student to complete in order to get from their initial answer to the optimal correct solution. This represents the student's knowledge state space. Second, tree-based Socratic questioning. Overall, each node in a tree represents a question, where an edge between 2 nodes indicates a path to new understanding. The instructor generates turn-level Socratic questions, conditioned on both the student's current knowledge state and their misunderstandings. This step is what dynamically constructs a Socratic question tree. We generate a sibling question when the student does not answer the instructor's question correctly. On the other hand, we generate a child question when the student answers the question correctly, but does not fully understand the target state variable. Third, adaptive conversation restructuring. The verifier updates the initial conversation plan based on how the student is progressing within the conversation, as reflected by updates, or lack thereof, to the student's current knowledge state. Additionally, if the student is stuck for a certain number of turns, then the instructor will trigger its teaching mode, where it simply teaches the student about the current knowledge state variable that it is guiding the student towards understanding. Each time the student resolves a state variable, we will ask them to provide any bug fixes, if any. Hence, the final output of TreeInstruct is the set of all bug fixes made by the student throughout the entire interaction. In order to evaluate TreeInstruct, we utilize a proxy student agent based on Mistral 7b Instruct. Our instructor and verifier agents use the same base model, either Llama 3.8b Instruct or GPT-4. We evaluate our method on 2 datasets, consisting of a student's buggy solution and the correct solution. We annotate each of the bugs as either a conceptual or syntactical bug. First, we use the Socratic debugging benchmark dataset, which consists of 149 problems. As these problems are relatively easy, with only 1 bug present, we choose to challenge TreeInstruct by constructing the multi-debug dataset. Multi-debug is based on 50 problems taken from LeetCode that are much more challenging and require more comprehension skills. For each of the 50 problems, we inject 1, 2, and 3 conceptual or syntactical bugs that a student would typically make, for a total of 150 different samples. we pose a mixture of quantitative and qualitative aspects to evaluate the effectiveness of the instructor-generated questions and overall conversation. For the former, we consider the relevance of the instructor's question to the student's bugs, whether it revealed either explicitly or implicitly the solution, and if it preserved the logical flow of the conversation. For the latter, we computed the average success rate of the student proposing bug fixes that are isomorphic to the ground truth bug fixes, as well as the average number of turns throughout the conversation. For baselines, given that this is a newly emerging area, we constructed an LLM vanilla baseline as well as adapted an existing single-turn method. For our results on the single bug Socratic debugging benchmark, we can see that TreeInstruct achieves the highest relevance, indirectness, and logical scores overall. While Vanilla GPT has the highest success rate for syntactical bugs, it also has the lowest indirectness score. This is because it posed very direct questions to the student and gave hints towards the bug fixes, which evidently increased the success rate. Nonetheless, when we evaluated the methods side by side, TreeInstruct was preferred over Bridge 79.43% more, and over Vanilla 77.43% more on average. On our multi-debug dataset, across all multi-bug settings, we can see an overall improvement of 16.6% and 11.59% in the success rates for syntactical and conceptual bugs, respectively. We can also see an improvement beyond baselines of 13.47% and 14.89% for syntactical and conceptual bugs across all three conversation metrics. Overall, TreeInstruct tackles challenging problems more effectively, maintaining its high performance despite problem difficulty increasing between the two datasets, as well as from 1 to 3 bugs being present within a student solution. In addition to using a proxy student agent, we also conducted a human case study where real human students across 5 different levels of programming experience interacted with TreeInstruct. The volunteers mentioned that TreeInstruct helped them learn programming concepts by forcing them to critically think about their mistakes, instead of just trying random solutions. Furthermore, all students with no knowledge of the system were not able to identify all of the bugs before their interactions, but ended up solving them independently under the Socratic guidance of TreeInstruct. Overall, TreeInstruct demonstrates that by integrating more structured representations of both student knowledge and the conversation state into educational dialogue, we can transform assistants into instructors, which guide students to critically think about their mistakes and arrive at solutions independently. Thanks for watching.